Hey guys, BuildZoid here, and today we're going to be taking a look at the RTX 2080 Ti Galax Hall of Fame OC Lab Edition card. Pictures were provided by Lucky Noob from Jagat OC, so huge thanks to him for sending them in, because these pictures were perfect. A lot of the time I get pictures which are borderline useless to me. These were great. These were exactly what I needed. These were perfect pictures. Everything worked out like awesome. And he has one of these cards because, well, this card's kind of special. So there's as far as I'm aware, they made 100 of these. And this card is required to enter the online qualifier for the Galax Overclocking Carnival this year. And so Lucky Noob is obviously, he's got one of these cards. He also bought the required memory kit. And so he's entering the competition. So, you know, good luck to him with that. You know, definitely a very cool event, and I really like, you know, I mean, good luck to win it. I'm kind of awkward. So anyway, back to the card. That's something I can't screw up, unlike, I don't know, what's it called? Social cues or something. Anyway, card is cool. Card is very expensive. It's also the limited, and you also can't buy it at this point because it's sold out. I really hate low volume limited editions, but I mean, I'm not going to miss this one because it was $1,700, so it's not like I was going to buy it even if they made more of them. Let's take a look at what it is that everybody will actually be competing on, because obviously there's, like, once you actually get to the OC Carnival, they're obviously going to be competing on yet more of these cards, or at least something that looks a lot like this card, because that's just how it's always worked with the Galax Overclocking Carnivals in the past as well, where, you know, you'd qualify on a Hall of Fame card, then you got to the competition, and guess what you were overclocking? More Hall of Fame cards. So let's see what everybody in the competition will be running, basically until the end. And let's start with the VRMs. So here we have the Vcore Part 1, because this is, of course, an RTX 2080 Ti, so the Vcore VRM is on either side of the GPU core. This has a few benefits. It spreads the VRM thermal, like it spreads the VRM's heat output over much more of the PCB, because instead of, like, if they wanted to, you could, in theory, like, put the VRMs in, like, 2 rows like this. Then you get this big hot blob on one end of the PCB. Now you have 2 hot blobs on the either end of the PCB. So marginally better thermals because of that. In theory, this could lead to slightly better thermal performance. The other big benefit to this layout is that basically when you have current flowing from the VRM, if you just had all of the VRM located over here, what you end up with is actually you get slightly higher voltage on this side of the GPU core than you get on this side of the GPU core, because obviously the further the current has to travel, the more resistance it has to pass through, and the lower the voltage level once it gets where it's going. So this has the benefit that instead of, you know, having like a voltage delta across the core like that, you get a voltage that's really low down the sort of the center of the core, because that's obviously where both of the VRMs are pushing to. And that could marginally improve overclocking performance. I think, honestly, NVIDIA designed it like this just because, well, this die pulls a ridiculous amount of current, and, well, actually, that probably was one of the considerations. It's just like we want to be able to get the VRM as close to the GPU core as possible, and putting a chunk of it right here is a really good idea to achieve that. So basically, it has some power benefits to sort of power quality, if you will call it that. That's a terrible term, but we'll roll with it. I should get the point across. And it does have some benefits for VRM thermals as well, because it does spread the VRM out a bit. Now, above Vcore VRM Part 2, I mean, wait, this is Part 2. That's Part 2 because it's smaller. So Part 1, above Vcore VRM Part 1, we, of course, have VMem. And that, of course, powers all of the GDDR6 memory chips right here. And other than that, on the card, which I'm not going to try to label, we have 5 volts, and we have 1.8 volts, and we have PEX, and we have 5 volts Part 2. Well, we have USB-C power, and at this point, we can actually refer to the voltage read points right here. So we have 5 volts, check. That's this point right here. Then we have 1.8 volts. We have PEX, which I'm going to assume is the PCIe voltage, because that's the PEX powers the PCIe interface. This powers the VPP rail of the GDDR6 memory chips as well as the BIOS chips. So that's going to probably be the PCIe V. Like Asus likes to call this PLL, so you know, the terminology for some of these voltages really depends on what vendor you're looking at. So I'm going to just assume that PCIe V is PEX rail. I'm not sure where that's located. Then they have a ground point right there. And they have 5 volts LCM. I'm going to guess that might be USB, I think. Why do they have 2 5-volt rails? Because they also have DR 5 volts. And I'm going to assume that's drive. So that's going to be like drive voltage. So that's going to be for like powering the these guys maybe? The thing is, like, these chips run off of 5 volts. Like, these definitely need a 5 volts rail. But I can't think of why you'd have 2 of them. Maybe for LEDs or something? I'm not entirely sure why they need 2 different 5-volt rails, but they do have 2 different 5-volt rails. Then they have, of course, GPU Vcore, 3.3 volts, DDR voltage, so that's the memory VRM, and yeah, the 5 volts LCM, which I assume is USB. So you have a whole bunch of different voltages. You get read points for all of them except 12 volts, which I guess the logic behind that is if you want to check your 12 volts, I mean, you can stab this, 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 and this, because there's actually 4 different 12-volt inputs on the card. So that's kind of a pain to check. Maybe would have been nice to have actual read points for those as well, but as it is, you know, you get all the ones that are sort of like all the minor voltages, you have them. I guess it'd be pretty obvious if you didn't have 12 volts. So that's the voltage monitoring points the card comes with, which is, of course, a feature for like extreme overclockers as well, because you can use a multimeter to monitor your core voltage and memory voltage and whatever other voltages you want to monitor. Because the software kind of sucks at that a lot of the time. So that's why that's there. And what else do we have? That covers all of the different VRMs. So I guess let's take a closer look at the Vcore monstrosity. How monstrous is it? Well, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 phases. Does it actually have 16 phases interleaving, though? No. And funnily enough, we can actually see that Galax at one point in time was considering running doublers, because that there is the, that's the component, like, that's the padding for a IR 3599. Like, that is totally a 3599 mount. I don't know why they didn't actually put one there, but that was definitely, that was meant for an IR 3599. The end result is that, yeah, they actually have some kind of, like, it's basically another one of these, you know, 2080 Ti oddity VRMs, where it's just like, there's not enough phases on the controller, and there's a lot of phases on the board. Now, the voltage controller on this card is, and here it's especially difficult, because, say, on the Asus Strix card, there's a really obvious, like, current monitoring. There's a bunch of current monitoring circuitry, which is really obvious, and you can clearly see that that's hooked up to 10 phases. And on the NVIDIA reference card, you can clearly see that they only have 8 phases hooked up. Like, they have current monitoring for 8 phases, which means they can only current balance 8 phases in the VRM. But here, that circuitry just isn't anywhere near the chip, so it's actually, like, I have no idea how much of it is hooked up, but I'm assuming that this is running in 10-phase mode, because the chip here is a XDPE 10281B from Infineon, and this doesn't have a public data sheet. But recently, Infineon, I did read a press release that Infineon has a lovely new, very expensive, very cool 10-phase voltage controller. And I'd have it as a guess that that is probably what that is, because that is one massive chip. And it looks like it probably has 10 phases. Unless Galax wants to run it in 8-phase mode and then decided not to run the 3599s, which is just kind of like, why not? Because they do have 8 of those. Like, there's 1, 2, 3, 4, 5, 6, 7, 8. So, yeah, I'm really not sure why they decided that they don't want those. Oh, I think I have an idea for why they might be 2 5 volts. They might have a 5 volt over here and a 5 volt over here. Maybe. Nah, they could probably, they'd just drag it across the board. That'd be silly to have 2 of them for that. Anyway, So you do, so this is probably running in 10-phase mode. Not sure without the card in hand. Which means there's probably something like, there's probably like, how would they work it? They'd have like 6 phases that are shared, and then 4 that are, because somehow you'd have like 12 plus 4. So you'd have 4 power stages that have each their own PWM signal, and then you'd have 12 power stages that are put in parallel. And that would be one way to hook this up. And then the power balancing could kind of dynamically change which phase has how much current going through it. Honestly, this is just like a really weird way of hooking up the VRM. But it is a way of doing it. It's just, it's not really a 16 phase because they're not, you know, they're not necessarily, they can't equally share out the load. Because, well, I mean, the controller could probably try to do that as well, but it's just more difficult than if you had like doublers proper. So it's kind of it's another one of these odd 2080 Ti VRMs where you just have way too many phases relative to how many the controller is actually controlling. But NVIDIA has done that in the past for power balancing purposes as well. So it's not exactly new, but it is weird. And I've still not figured out how I'm going to judge this. But still, 10-phase controller is really neat. So I'm just going to say that's great. They have the 10-phase controller. And then for the actual power, for the phases themselves, they're using a Infineon power stage, which is the TDA Smart Power Stage, TDA 21470. And this is, of course, a 70 amp power stage. And it's a smart power stage because it integrates temperature monitoring and current monitoring directly into the chip, as well as overcurrent protection and over temperature protection. So basically, these will shut down if you try to overheat them or overload them, which technically overheating is a side effect of overloading, but you get the idea. It'll shut down if, like, you could be really cold, and if you push too much current through it, it'll shut down for safety, regardless of how cold it is. And if you have it too hot, well, it'll shut down because it's too hot. So it'll shut down for both possible, like both high risk scenario, like high probability of damage scenarios. And the interesting thing about the TDA 21470 is that it actually has very, very, if not, well, pretty much identical efficiency to the CSD 9. And I just realized I should probably, give me a second. Yeah, it is 95480. 95480 power stage from Texas Instruments. Like, the efficiency between this thing and this thing is the same. And why am I pointing that out? Because this doesn't have a public data sheet, but this does. Though, admittedly, this public data sheet isn't particularly detailed. It is at least public, unlike this one, which I have my sources, is what I'll put there. So the efficiency between these two is and I've just screwed up my paintbrush, so that's great. The efficiency between these two is very, very similar. And so I basically just copy-pasted all of the VRM thermal performance figures from my Strix video, because like the power stages match up, and there's the same amount of phases, and they're both 10-phase control as well. So then, VRM efficiency, what are we looking at? Well, since this is one of these new 70 amp power stages, you can bet that it's spec'd at 1.8 volts, because these are designed for Intel's integrated voltage regulators, not for NVIDIA GPUs. And I've scaled it down to 1.2 volts using an International Rectifier 3575, just because I have a complete data sheet for that. And for the switching frequency with these, we're looking at 600 kilohertz. Which is even higher than like what the FDMF 3170 that you would find on the reference cards have. And honestly, these two are slightly ahead on efficiency compared to the Fairchild Semiconductor FDMF 3170. So the FDMF 3170 is what you actually get on like a reference 2080 Ti or the MSI 2080 Ti, the Gaming X Trio card. And that is still a 70 amp smart power stage. It's just slightly worse than these two. These are slightly more efficient. And this card has more phases than the MSI or the reference. So that's also worth noting. But it's the same number of phases as a Strix. Probably with the same wiring situation as well. Now then, for 200 amps output, you're going to be looking at a 1.8 volts VR heat output of about 17 watts, and at 1.2 volts, only about 14 watts, which is like, that's amazing. Like, there are motherboards that put out 14 watts at 100 amps, right? And this is doing twice as much current at 14 watts. These things have peak, like, the CSD 954480, like, it prides itself on basically maintaining over 95% efficiency up to 30 amps output, which is ridiculous. And then the TDA 21470 has a peak efficiency of 96%, and also does like 95% efficiency all the way up to 30 amps, which is just like, again, just equally ridiculous. These are basically the same chip, just made by like different companies. One of them might be more expensive than the other. But anyway, the end result is that you get some absolutely ridiculous... Like, the amount of heat this VRM produces for some insane current outputs is really low. And basically, 200 amps output on this VRM, you shouldn't even need a heatsink at all. Like, the power stages themselves have so much surface area, they should be able to deal with it on their own. You don't need to really worry about it. Now, 300 amps output, we're still talking about very, very low heat outputs, about 26 watts at 1.8 volts, and only about 21 watts at 1.2. All right, again, with just how many phases you have and how far apart they all are, this should just have no problem cooling itself without really any, with maybe just like a gentle breeze going past them. Now, going up to 400 amps, at this point, you might actually start considering getting a cooling system for the VRM, because at this point, it'll start producing about 37 watts at 1.8 volts, or about 30 watts at 1.2, which is still not that much. Going up to 500 amps, and at this point, you know, like, this is very much LN2 territory, or dry ice. So 500 amps output, you'd be looking at about 48 watts of heat output, or 40 watts, well, 39, but I just wanted to round it up, but about 39 watts of heat output at 1.2 volts, 600 amps, which is, mind you, 1080 Ti's would generally be in somewhere in that range on LN2. A maxed out 1080 Ti would be between sort of 400 and 500 amps, really averaging closer to the 400 than the 500. It would peak up to 500, but it would really average around 400. So 600 amps output, you'd be looking at about 69 watts of heat output for the 1.8 volts, and about 55 watts at 1.2 volts. Which is just like, it's still so very little heat here, right? And then at 700 amps, which this is where I really like, there's no way a 2080 Ti is pulling more than that. It's like on a theoretical level, I don't think it's going to do more than that. 96 watts of heat at 1.8 volts, 77 watts of heat at 1.2 volts. But as I said before, these are exactly the same figures that I used for the Strix card, because these two power stages have basically the same efficiency as each other. As in, you can take the efficiency curve for this thing and put it over the curve for this thing, and they look at like, well, they'll be on top of each other, literally right on top of each other. So, yeah, still really impressive VRM. But the thing is, you can get the same VRM efficiency on the 2080 Ti Strix from Asus. But this is where so the actual power capability here and the VRM efficiency, like, Galax doesn't really have anything super special in that department. In the past, like with the 1080 Ti, they had the only good 16-phase 1080 Ti that I'm aware of. I know Zotac had a 16-phase, but they used like the cheapest and worst MOSFETs they could get their hands on. So yes, they had a lot of phases. Each of those phases was really, really bad. Here we have 16 phases that are better than, like, honestly, up until recently, 70 amp power stages straight up didn't exist. So this is top of the line phases. Like, each of these phases is more powerful than any phase produced in the last couple years, with some exceptions where manufacturers would like double up on really high-end power MOSFETs and that kind of thing. But those were like exceptions, not very common. This is, as far as power stages go, it doesn't get better than this. So this is, it's the best 16 phase, but the Strix has the same VRM here. So the difference with the Galax card here is is compared to the Strix, Galax has gone way more output filtering. I mean, they've just gone absolutely overboard. Every inch of space that they could fill with multi-layer ceramics has been filled with multi-layer ceramics. I mean, look at that. Ceramic City. And another big interesting difference from the in the capacitor selection is these two right behind the core. Most of the other 2080 Ti's I've seen so far opt for a bunch of multi-layer ceramics. This one, as you can clearly see, has two 560 microfarad, I'm assuming aluminum polymers. They might be tantalums, but I'm guessing these are aluminum, not tantalums. And I'm guessing that based on the fact that I've seen aluminum, like, you can get aluminum polymers in much, much lower ESRs than you can get tantalums. The biggest benefit with a tantalum capacitor that, like, I've seen when just looking through various capacitors for, like, my modding adventures has been that you can get, like, some insane amount of capacitance on tantalum capacitors compared to aluminums. Like, in the same size packages like these guys, you could probably get a tantalum that goes like 1,000 microfarads, but it would have much worse ESR. So for the purposes of, like, sitting right behind a GPU core, I would assume these are aluminum polymers, not tantalums. But, you know, without a bill of materials, I'm not 100% certain, but that's just my best guess. And so, yeah, Galax has just gone, like, you know, loaded the card with capacitors. And then, of course, on the front of the card, we also have these Nichicon FP series aluminum polymers. And Asus also has those, except they've, like, not bothered with, like, all of these ceramics. They do still have the SMD caps that you can see here, right? Asus also has those. I think they might have less of them, though, but they don't have the multi-layer ceramics in between them. And they also use smaller bulk capacitor. Well, this is technically a type of bulk capacitor as well, but the really big bulk capacitors here are even bigger. These are 1,200 microfarad instead of just 120, though I'm not sure how many there are. So basically, Galax has a slightly different output filtering for their VRM. I'd say better output filtering for the VRM, as well as slightly maybe better filtering on right behind the core. So yeah, they, like, efficiency wise, this is no different from a Strix. Filtering wise, they've, you know, basically maxed it out. Like, there's no space left on this card. The only way you could get more multi-layer ceramics on here is if you started stacking them, which is not practical in the slightest. So yeah, this is just Galax, and they've done this on the past Hall of Fame cards as well, where they just, like, oh, there's free space on the PCB, load it with capacitors, because what else are we going to do with it? They've basically taken my approach to GPU modding. It's like, oh, look, there's space we can put capacitors in, let's put more capacitors in. How effective that may be, I'm not sure. Generally, in my experience, it hasn't helped much. But, you know, who knows? It might have worked out for them here. And they've done the same thing on the memory VRM. Like, that memory VRM's output is, again, just loaded with extra capacitance. So yeah, and on the input, they kind of have the same thing going on with a whole bunch of large multi-layer ceramics for 12 volts right there. And then, of course, you have just as much space as can be used filled with yet more bulk capacitors for 12 volts. So Galax is basically going just like, well, if there was any free space we could find, we filled it with capacitors, so there's no more free space. In theory, that does mean the card could clock a little bit better, even though it has, like, the same VRM as the Strix otherwise. So it's basically the Vcore VRM. What I consider it here is basically a slightly upgraded Strix VRM. Marginally so. I don't think you would notice it. Well, on LN2, it might actually make a difference. In other, like, normal applications, I have a hard time believing that it would make much of a difference. Especially on, like, air cooling or water cooling, or maybe even dry ice. Like, dry ice, I'm not sure you'd notice anything. But LN2, there it might start actually having a pretty major impact. So it's like the big thing that's kind of Galax has done, because otherwise this is really just a Strix VRM. So moving on from the Vcore, let's move on to the VMEM. And this is where things get a lot less nice. Where the Vcore VRM is, you know, there's two cards with a VRM this powerful. This card and the Strix. When it comes to the memory VRM, Galax has gone for their standard, but unfortunately disappointing, in this case, 3-phase. We have 1, 2, 3 phases. It's controlled by this chip right over here, which is a downgrade. This is a UP9509, whereas everybody else is either running a 9512 or an MP2888. And the thing is, the UP9509 it's an analog chip with just PWM vid on it. So if you want to change switching frequency or load line or literally anything, you need to do it with resistors around the chip. You can't just set it. It integrates 2 drivers, and you also have a driver over here for that, and another driver over here, because obviously we have 3 phases. We need 3 drivers. No weird, you know, phase sharing thing going on here. And the thing is, they've opted for discrete MOSFETs. And, well, these aren't great. I mean, this is pretty much half the Vcore VRM of an RX 480. But let's just put it this way. The best RX 480 VRM is around 60 amps per phase. Like, has 60 amp per phase power stages. That's the best RX 480. This is what you would find on an reference RX 480. This is a 70 amp power stage. Most other 2080 Ti's take this 70 amp power stage and just put it into every single one of the VMEM phases. And that's just kind of what they roll with. So Galax going with the MDU 1511 and the 1514 is actually rather disappointing. Because, like, don't get me wrong, it's not like the memory VRM is underpowered. It's still way overkill for the amount of power that the GDDR6 will use. It's just, like, this card is supposed to be, like, the best, right? As far as I'm concerned, this is supposed to be the best. There shouldn't be another card where it's like, oh, this is better. On no competitor's card should have anything better than this does. And yet, this memory VRM is less efficient than literally every other 2080 Ti out there, including the reference card. It also has a slightly worse voltage controller than every other 2080 Ti out there, including the reference card. So at that point, it's just like, I'm disappointed. Because, the end result, and mind you, the end result is really not that bad. I mean, what we're talking about here is for 20 amps output at one point, and I've run out of space in that area. So, just powering the memory chips, right? 500 kilohertz switching frequency, because that's what the power stages regularly run at, or 600 kilohertz in the case of these guys. So 500 kilohertz, 1.35 volts output, and I'm assuming here 12 volts gate drive, so 12 volts gate to source. If they're running them on less than that, then the efficiency gets even worse. So 500 kilohertz, 1.35 volts. 20 amps output, you're looking at about 2 watts of heat, which is actually exactly the same as what you get with all of the other 2080 Ti's, so that's not a problem. But at 30 amps output, this produces a whopping 3.5 watts of heat. Which is why I said, like, it's not like this is doing badly. I mean, it's still massive overkill, right? This is going to run passive. It's not going to have a problem getting cooled. The problem is that most other 2080 Ti, like all the other 2080 Ti's, do 30 amps at 3 watts, not 3.5. So that already is just like, you know, like that's a slight downgrade. And then 40 amps output, which I don't think, like, the GDDR6 shouldn't necessarily hit that unless you're overvolting it, which I'm not sure if it even scales with voltage. At that point, this would be producing about 5.5 watts instead of 4. And, yeah, so it is very, like, well, it's not even slightly, like, 5.5 watts compared to 4 watts, that's percentage-wise, that's a pretty major difference. It's still completely irrelevant, because you're still not going to have any problem cooling this. It's just really kind of disappointing that, you know, the Hall of Fame card here has a memory power system that is slightly worse than everybody else's. Not relevantly so, right? Like, as I said, like, this is not going to cause any issues under any conditions, really. I honestly, I'm more annoyed with the voltage controller being a downgrade, because maybe, just maybe, cranking up the switching frequency on a UP9512 all the way to the like 1 megahertz or 1.5 megahertz where the power stages max out, could actually maybe help with memory overclocking a little bit. And that is straight up not possible with the UP9509. It doesn't go up to switching frequencies that high. But the VRM efficiency, like, that's not really a huge issue. But basically, I'm just not impressed by the memory VRM. It's still plenty powerful, and I'm 110, like, I'm almost 100% certain that even if you did take another card and just took a reference card and just smashed the switching frequency on that VRM, and just ran it as hard as you could, you still probably wouldn't get the memory to clock any better than this does. But it's just like, why couldn't you just, like, this thing is so expensive, right? So freaking expensive. And it's a 100 units limited run. So I don't see a justification for, you know, downgrading the MOSFETs, downgrading the voltage controller. Like, why? You know, it's like the reference card uses a better voltage controller, and the reference card uses better freaking phases. So, yeah. Very, very minor downgrade, right? Like, don't get me wrong. Very, very minor. But it's still a downgrade. Like, it just is. So that is rather disappointing. Well, other than that, it's, you know, it's still a solid memory VRM. But, yeah. Just a little bit disappointing. So, you know, for the main VRMs here, we have the Strix Vcore VRM on steroids, and a slight downgrade compared to every other 2080 Ti out there on the memory VRM, but a downgrade that's quite frankly almost certainly irrelevant, as in it doesn't actually make a difference that they've downgraded that part. So, VRM-wise, very, very, very impressive. Now, how does power? Now let's look at the sort of the other stuff on the card. So this being a 2080 Ti, it of course has two NCP 45491s, 45491, and these are the current monitoring chips. So these guys monitor things like this shunt here, that shunt there, that one over there, this one down here, this one, and like this one, and is there any more of them? There should be more of them. Somewhere. Well, I can't find the rest, so that covers the one I could... oh, there's another one. So you have just a bunch of shunts just scattered all around the card, and then you have a bunch of random sort of transistors for power balancing everywhere, along with UP76501s, which I can't find, but they look kind of like that, so that's probably one of them. You also have these two big power MOSFETs over here, which I assume are probably also for current balancing. As I can't really think of what else they would be for. So in typical sort of NVIDIA, you know, 2080 Ti fashion, and then you have these guys for current balancing. So you have just current balancing circuits everywhere, which is standard for these cards because, which are all controlled by the 7651s. And the reason why that exists is because NVIDIA has a per power connector power limit. So in theory, you can end up in situations where you're maxing out the power limit on one connector without necessarily maxing out the power limit for the whole card. And in that scenario, the power balancing circuitry will take some of your phases, take some of the phases from one of the connectors and put them on another connector to prevent that situation where you're power throttling because you're overloading one of the connectors. Well, bouncing off of the power limit for one of the connectors. You're not necessarily overloading the connector because the power limit is probably way too low to even get anywhere near overloading the connector, but you get the point, right? So that's pretty much the standard 2080 Ti loadout. And then what Galax has added on is the bunch of jumpers just about everywhere, which I assume are for just disabling all of that, which I'm very pleased with. That is a design decision I fully support. This would be like one of the first things I would do with the 2080 Ti if I got my hands on it, would just be remove all of NVIDIA's fancy power management technology. It's just like, assuming that it doesn't break the VRM somehow, because I'm not like, it might affect the phases negatively, maybe. Not 100% sure how specifically that is hooked up and how it's supposed to work, but assuming I can remove it, I'll remove it, and I assume that's what the jumpers do. So that's kind of that's kind of interesting. You can clearly see that, you know, one of those extreme overclocker things added to the card. And then of course you get this weird connector over here, which is for a little controller add-on that the card comes with, which plugs in onto there, and it gives you voltage controls, and I assume load line controls and switching frequency controls, and power limit probably you could lift the power limit with the jumpers. So basically you just get all of your you know, overclocking controls. Like, it would also have memory voltage control, and I assume PEX rail and 1.8 volts control as well, unless those two are irrelevant to LN2 overclocking again. So yeah, that is kind of the Hall of Fame. And quite frankly, it's kind of like a Strix. So it's like, if you want a card that most closely resembles the 2080 Ti Hall of Fame, just get a Strix from Asus. The main downside to getting a Strix is that you're not going to have the extra 8-pin power connector, which, like, and you're not going to have all of the extra extreme overclocking functionality, like the voltage read points, the jumpers to disable all the stupid power management. Well, I assume they're for disabling all the stupid power management crap, and the convenient sort of voltage controls. You're going to have to get mods for everything unless you get your hands on an Elmore EVC and hook that up to the card. So that is it for the 2080 Ti Hall of Fame. You know, I'm kind of sad that I can't just sing praise to it, because that's what happened with, like, the 1080 Ti Hall of Fame, where they just went absolutely, like, that thing was undisputed. Like, that was definitely the best 1080 Ti PCB out there. The Kingpin edition still managed to, like, you know, keep up with it, no problem. But it, because, you know, there's a point of diminishing returns, and once you, well, it's like there's actually a point of no returns, right? Like, you can keep upgrading the VRM. At some point, more upgrades aren't going to make the chip clock any better. Okay, you're just going to max out on how good the VRM can be, and then it's over. You're not going to see any more improvement going further than that. And that was very much the case kind of with the 1080 Ti Hall of Fame. And here, I mean, it's still really, really nice, but it's just like, it's not quite as much of a jump from all the other cards as it was with the 1080 Ti, right? Because you can get as I said, like, a Strix basically has the same VRM. And honestly, even the reference card has a 13 phase, right? Like, whereas if you compare it to, like, on the 1080 Ti scenario, right, the reference 1080 Ti is a 7-phase. The Galax card was a 16. The Hall of Fame was a 16. And here, it's just like, yeah, so you went from a 13-phase to a 16-phase. The power stages are a bit more efficient than what you get on the reference card. The memory VRM got a downgrade, and then you got a bunch of extreme overclocking features. It kind of feels a lot less epic than in the past, which I'm just kind of sad about. So that is now finally it for the video. Thank you for watching. Like, share, subscribe, leave comments, questions, suggestions down in the comment section below. Also, one last thank you to Lucky Noob for, you know, providing the photos here, and good luck with the qualifiers to him. And yeah, that is it. Oh, and if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. And there's also t-shirts you can buy. You can find a link to all of that down in the description below. And that is it. So I'm going to go hit that stop button before I remember something that I forgot and, you know, start rambling about that. And I'm really going to stop.